Hello everyone. Today we will discuss about polymerization shrinkage. We will talk about how polymerization takes place and what leads to polymerization shrinkage, what are the methods to prevent the shrinkage, and how to take the advantage of the polymerization shrinkage which is inherent in the composite resins. So starting with the introduction. So the most universally used direct tooth color restorative material introduced by R.L. that is a composite resin, is widely used in restorative dentistry. It has got acceptable aesthetics and it can be directly bonded to the tooth structure without removing much of the healthy tissue. But polymerization shrinkage stress has concerned clinician and researcher since they were introduced into the dental practices. So what is the basic formulation of the composite resin? It comprises of a matrix, that is an organic resin. They vary in their composition and they consist of bisphenol A glycidic methacrylate, urethane dimethacrylate, triethylene glycol dimethacrylate. The triethylene glycol dimethacrylate is a low viscosity monomer which are incorporated to reduce the viscosity of the resin and facilitate the handlings. Next content we have the inorganic fillers. Right, so they comprises of the quartz and the colloidal silica, and these fillers significantly improves the material properties such as hardness, thermal stability, radio opacity, water absorption, viscoelasticity, creep, etc. etc. Right, so we have a material to bond the matrix with the inorganic filler. And what are those agents? These are the coupling agent. The coupling agent is used to bond the filler particle with the resin matrix. This filler particle is bonded to resin matrix with the use of coupling agent. So what are the coupling agent commonly used? They are the organosilanes, that is the gamma meth acryloxypropyl trimethoxysilane, zirconates and titanates. Apart from this, we have activators. In visible light activator system, it consists of a single paste which has got camphorquinone and tertiary amine, that is the dimethyl aminoethyl methacrylate. And when the camphorquinone combines with the DMA, it forms a complex as it breaks down and releases the free radical. So in this way, in light cure activator system, the free radical is generated. And in the chemical cure system, we consist of a two-phase system in which we have a benzoyl peroxide, and in other we have tertiary amine, that is the N-dimethyl paratoluene. These two interact and they generate the free radicals. So in this way, they lead to polymerizations. So to prevent the spontaneous polymerization of the monomers, we have something called as the inhibitors, which function is to inhibit the chain propagation by terminating the polymerization process. So butylated hydroxytoluene in a concentration of 0.01% by weight is used as inhibitors. So how free radicals is brought about in 4 different ways. Let's discuss it now. In heat activator system, the benzoyl peroxide splits under heat exposure and forms a free radical. Whereas in chemical activity system, a tertiary amine is used to split the benzoyl peroxide system into free radicals, about which we have discussed just now. In UV light activator system, we have a 365 nanometer UV light source which splits benzoyl methyl ether into free radical without the presence of tertiary amines. And in light cure system, as we have discussed, it comprises of camphorquinone and non-aromatic tertiary amine, that is N-dimethyl aminoethyl methacrylate. They combine together and they generate the free radicals. So this is a chart describing the summary of the same. That is in heat activity system, benzoyl peroxide in heat generates the free radicals, and in the chemical, the benzoyl peroxides and 2% aromatic tertiary amine generate the free radical. In UV light, 0.1% benzoyl methyl ether and 365 nanometer UV light source. In visible light system, we have camphorquinone and aliphatic tertiary amide, which will generate the free radical system. So till now we have generated the free radical. Let's now discuss how polymerization occurs. So what is polymerization basically? During polymerization, the monomer is getting converted into polymer. So for this we require something that is called as the free radicals. And what these free radicals do? The free radicals give energy. The free radicals give energy to the monomer, and this monomer is getting converted thereby into the polymer. So this is how polymerization occurs. So the generation of the free radical is going to decide whether it is the light co-activity system, heat co-activated system, or UV light and chemically cured. So this is a chart describing the polymerization process. So here you can see that we have the initial monomer, and the free radicals react with the initial monomer, and the chain propagation is initiated. Again, new free radicals combine with the monomer, and in this way the chain is propagated. So in the initiation process, we have the free radicals reacting to the monomer to form the initial end of the polymer, chain. And in the propagation, we have the addition of the monomers. To the growing chain. And so what is this termination step? In termination step, there is a conclusion of the process as a result of steric hindrance or depletion of the monomer. Obviously, we need to stop the spontaneous polymerization and inhibit the chain propagation. And the term used for this is the termination of the polymerization chain. So this is a chart describing the polymerization process. So at what point the shrinkage occurs? So during the polymerization process, the weak van der Waals forces keep the monomer groups, and the distance between the two monomer is about 4 angstrom. Right? But during the polymerization process, these forces are substituted by the covalent bond, which now have a distance of approximately 1.5 angstrom. So consequently, volumetric shrinkage occurs. Generally, it is less than 1% up to 6% depending on the formulation and the curing condition used. So what is the origin of the shrinkage stress? Is it lie in the basic formulation, or it occurs during the polymerization process? So shrinkage stress development, first we have boundary condition and the amount of the material. Under this we have the C factor. C factor is the ratio of the bonded upon the unbonded surface. The more the bonded area, the higher the stress level. On the contrary, the higher ratio of the unbonded to the bonded surface, the less the C factor, and the more the area the polymer can flow through, hence the less generation of the stress. It is interesting to note that the polymerization shrinkage creates stress as high as 30 megapascal between the composite and the structure. Now next is the composition of the resin and the resin materials. So obviously there must be something that lies in their composition that leads to the polymerization shrinkage stress. Yes, the higher the molecular weight, it will result into lower shrinkage value than those with the monomers having the low molecular weight. Right? Also, the concentration of the inhibitors also has an effect. The inhibitors concentration reduce the rate of polymerization and the shrinkage stress without significantly comprising the final degree of conversion of monomer to polymer. Right? And one more thing, the filler ratio. The greater the composite filler ratio, the greater the elastic modulus of the composite. Consequently, stress development will be higher and shrinkage will be more. Right? Next, coming on to the material properties. Yeah, there are the three inherent properties: the volumetric shrinkage, the degree of conversion, and the elastic modulus. These are crucial over the magnitude of the stress. The complexity of the polymerization shrinkage stress relies on the fact that these three factors are interrelated, and it is very difficult to segregate between these factors. Coming on to degree of conversion. So what is degree of conversion? Degree of conversion is the percentage of carbon-carbon double bond that has been converted into single bond, right? The double bond that has been converted into single bond. So this is basically the degree of conversion that we are talking about. Okay, a conversion of 50 to 60% is typical of highly cross-linked based TMA based composite. Implies that 50 to 60% of meth acrylate groups have polymerized. Right, but what about the rest, the percentage which have not participated in the cross-linkings? Do they do not participate, or what is the function? See here, this is the basic structure of a dimethacrylate monomer. We have a 2 carbon-carbon double bond. This is one, and this is another. Say one carbon double bond has participated in forming the crosslink, and another one, that is an unreacted pendant methyl double bonds. This is still left, and it could still covalently bond to the other polymer structure, right? And it forms a pendant group. The function of this pendant group is to plasticize the resin and soften and swell the resin structure. Then the cross-links one group strengthen the composite resin. Next is how to evaluate the polymerization shrinkage stress. So we have different apparatus, that is a mercury dialectometer. This is the equipment which evaluates the volume change in the mercury column, which is surrounded by the uncured composite resin. The change in the mercury column depicts a polymerization shrinkage strain. Next is the bonded disc method for evaluation of the shrinkage strain. In this, a disc-shaped specimen of uncured resin is placed in the center of the square cross section of the brass ring, and we have a linear variable differential transformer which is positioned to measure the plate deflection. Other simple methods to determine the post-gel shrinkage was developed by Sakaguchi using a strain gauge techniques, and apart from this we have a linometer which evaluates the linear displacement of thin plate position in the resin composite surface, and we have Kakabura et al. Which uses X-ray microtomography to evaluate the three-dimensional marginal adaptation. Next apparatus is Biomass stress measurement device, extensometer apparatus, that is connected to universal testing machines. Apart from this, we have an optical method. What happens in this optical method? An uncured composite sample is placed over a non-stick silicon surface under a stereo microscope. The image is taken before and after light activation at the same magnification. After using image analysis software, the sample outline before and after polymerization is determined, so that we can evaluate the changes in the surface area, and how much polymerization shrinkage has occurred can be calculated using the image analysis software. Next is the finite element analysis, or the photoelastic method. This is a valuable tool for examining the magnitude and distribution of the shrinkage stress. Different area depicts the different magnitude of the stress generated. Apart from this, we have crack propagation in a glass cavity. This method is based on measuring the residual stress in bonding substrate by using the increasing length of indentation cracks performed at the margins of the filled glass cavity. Next is the CUSPAL fraction. The polymerization shrinkage can cause CUSPAL fraction, And obviously this CUSPAL flexure is a detectable indication of the influence of the internal stresses that are generated by the teeth substrates in order to resist the shrinkage movement. And this cusp deflection can be measured by strain gauge apparatus at the external cuspal surface. Apart from this, we have enamel crack tracing. The crack propagation has been associated with shrinkage stress development, and this stress generates the microfractures, and the fracture line generated corresponds with the area of expected having high cuspal strain. So what are the strategies to reduce the shrinkage stress in clinical procedures? So either to change the material formulation or the mechanism of initiating the polymerization. So the first one that is commonly used is the incremental layering technique. What we do in incremental layering technique, that instead of placing the composite in one go or in one shot, we place the composite layer by layer, either in oblique layering technique, U-shaped layering, vertical, or in the two-layer techniques. So why do we do that? What's the advantage of placing composite in increments? First of all, the rationale behind this is that at each part, after each placement, after each incremental layer, we have few bonded cavity walls, which is involved at the each stage of restoration procedure. So more of the area remain unbonded to relieve the shrinkage stress development. And it also enhances the degree of cure, as only a thin section can undergo high degree of cure due to lower light attenuation, and thus the net degree of conversion is greater in the incremental layering technique. Right. Next is the stress absorbing layer or the intermediate layer placement. There is a concept of elastic wall cavity. Before discussing about this, basically what happens in the polymerization process of the composite resin? The composite resin transits from a viscous liquid into a viscoelastic solid, right? The point at which the resin starts to develop the elastic properties is defined as the gel point, and as the polymerization process proceeds beyond this gel point, vitrification occurs. That is, vitrification is a point where the resin can be considered as a solid. So there is a transition of the resin from viscous liquid into viscoelastic solid. So we will take cue of this concept in the later methods to reduce the shrinkage. Right, so now coming on to the topic, that is the elastic cavity wall. So what we do in this concept, we place an intermediate layer having lower elastic modulus, which act as a stress absorber, and it reduces the shrinkage stress generated. For this we place adhesive layers, that is a glass ionomer or a flowable composite, which is having generally less modulus of elasticity, and this will reduce the shrinkage stress whenever the stress is generated. So it is absorbed by the intermediary layer. Next we can modify light curing protocols. We can either have a soft start, that is the curing will begin at low intensity initially and it will finish off with high intensity. Next is ramping, and during ramping the intensity is gradually increased or ramped up during this exposure. Such ramping employs stepwise linear or exponential modes. Next is a delayed curing. The restoration is initially incompletely cured at low intensity, and then we take a pause, that is the clinician can utilize a time period in sculpting and contouring the resin to the correct occlusion, and after doing this we can apply the second exposure of light for the final cure. This delayed curing is also called as a pulse cure. This often reduces the white halo white lights that is seen during the seen at the margins. So this is one of the light curing protocol that is very useful in reducing the shrinkage stress. Next is the modification in the restorative composite formulation. So under this we have a siloline system that has been developed to minimize the polymerization shrinkage. It provides high performance bond to the tooth structure. So what magical content is there in the siloline system? So what is so unique about this siloline system? The siloline system is designed to minimize its shrinkage and the polymerization stress. In the conventional methacrylic based resin, we have a linear free radical addition, that is the monomers come close together to form the bond, isn't it? The monomer come close together to form the bond. Yeah. This process result into loss of the volume, hence the polymerization shrinkage. Yes, but in contrast to the linear reactive groups of the methacrylate, the ring opening process of the siloline based system is unique. So what happens in the siloline based system? The polymerization starts with the cleavage and opening of the ring, and this process gains space. Obviously it is opening up and this will gain the space. So this process gains space and this will counteract the forces that is going to generate in the subsequent step, isn't it? So when chemical bonds are formed, in total we have a reduced volumetric shrinkage as compared to the conventional system. So this is the advantage of using siloline based systems. Next is the use of bulk fill composite. Bulk fill composite resin have a better and greater degree of conversion than the conventional one, and the reason lies behind the fact that they have got the larger filler size of more than 20 micrometer, right? More than 20 micrometer. The composition of the bulk, so the difference in the composition of the bulk fill materials leads to a lower total filler matrix interface, and we know that the lower the total filler matrix interface, the lower the generation of the shrinkage stress, and consequently less shrinkage development. So this enhances the amount of transmitted curing light and reduces the scattered light, resulting in high degree of conversion of the large filler containing resin based composite. Also, this bulk fill composite resin reduces the post gel shrinkage. That the concept that you have just discussed, that the resin gets converted to viscous liquid, get converts into viscoelastic solid. The gel point is the point where the first is the point where the resin get converted into solid, where the resin start to develop elastic properties, and as the polymerization process proceeds beyond the gel point, the vitrification point occur, that is the resin get converted into solid form, right? So this reduces the post gel shrinkage method, that is after the gel point, and it also reduces the CUSPAL deformation, shrinkage stress, and the fracture resistance is increased when compared to the incrementally filled teeth. Next is the delayed activation of the dual curve resin. So it has been demonstrated that a delayed time of 3 or 5 minutes prior to light activation of the dual curve cements can reduce the shrinkage stress and improve the bonding strength without significantly altering the mechanical properties. Right. Next is the preheating concept. This concept is basically a theoretical concept, and it is not used clinically in practice. So the rationale behind this is that on increasing the polymerization temperature leads to lower the viscosity of the resin material, and this will increase the mobility of the material, mobility of the monomers, and the more free radicals is generated in the matrix resin, so it results into higher degree of conversion. Right. It is simple, that is, on increasing the polymerization temperature leads to lowering the viscosity of the resin materials, and lowering viscosity increase the mobility of the monomer molecules within the resin matrix system, and in this way the more free radical is generated. So these are the techniques to compensate the polymerization, to decrease the polymerization shrinkage. So that's all for today. Thank you.